Welcome to the Public Exam Review for Advanced Math 3200. We will continue with the review on Chapter 8, Logarithmic Functions. In this presentation, we will use various formulas to evaluate some simple logarithms. Here we will focus on evaluating logarithms using a variety of methods. Just a couple of methods that we will focus on. We have to remember how to switch from exponential form to logarithmic form. So if the exponential form is of the form a raised to the power of b equal to c, then we can say that the log of c to base a is equal to b. Another important property of logs that we will use is if the log of c raised to the power of k to base c is equal to k. In this case here, this is a very important property that we will use often. So if we can get the base of our logarithm to be the same as the base to our power, then the answer is just equal to the exponent k. As well, another property that we may use, if the log of a to base c, then we can rewrite that as the log of a divided by the log of c. Let's look at some examples. Here we are asked to evaluate the log of the square root of 32 to base 2. Notice that the base to the logarithm is 2. Is it possible for us to write the square root of 32 with a base of 2? So let's try. To begin with, we will get rid of the radical sign by changing the square root of 32 to be 32 raised to the power of 1/2. The number 32 then can be expressed as 2 raised to the power of 5, all raised to the power of 1/2. Here we have a power of a power, so we can multiply our exponents. So we have the log of 2 raised to the power of 5 over 2 to base 2. Notice now that we have it of the form the log of c raised to the power of k to base c. In this example, the answer will just equal the exponent 5 over 2. So that will be the final answer for this equation, or this expression. In the next example, we are asked to solve for x. Here we have the log of x to base 27 is equal to 2/3. In order to solve for the argument x, we need to convert from logarithmic form to exponential form. So we would say that 27 raised to the power of 2/3 is equal to x. Now we have a fractional exponent, which we can change to a radical. 27 to the power of 2/3 can be written as the cube root of 27, which we can find, and then we'll raise all of that to the power of 2. The cube root of 27 is equal to 3, raised to the power of 2, and our final answer will be x equals 9. In the next example, we are asked to solve for x. This time, x is the base to our logarithm. Remember that the base to the logarithm cannot be negative, and it cannot be 0, and it cannot be equal to 1. So the value of x has to be positive, but it cannot equal 1. Here we have the log of 5 to base x is equal to a negative 1/4. Once again, we will convert this from logarithmic form to exponential form. So we have x raised to the power of negative 1/4 is equal to 5. Essentially, what we're looking for here is x raised to the power of 1. So what we do to one side of an equal sign, we must do to the other. In this case, we will raise both sides of this equation to the power of negative 4. So on the left-hand side, we have a power of a power, so we can multiply our exponents. Negative 1/4 times a negative 4 is a positive 1. So we have x is equal to 5 raised to the power of a negative 4. Using our rules for exponents, that's equivalent to 1 over 5 to the positive 4. X is equal to 1 over 5 raised to the power of 4 is equal to 625. So that is our value for x in this example. Let's continue. Here we are asked to evaluate 5 raised to the power of the log of 1 over 16 to base 2. In order to answer this question, we need to do a little bit of work with the exponent. So let's let the log of 1 over 16 to the base of 2, let it equal a variable x. Converting to exponential form, we have 2 raised to the power of x is equal to 1 over 16. And we can write 1 over 16 with a base of 2. 16 is the same as 2 raised to the power of 4. So 1 over 2 to the 4 can be written as 2 to the negative 4. Now we have 2 powers with the same base are equal, therefore the exponents must be equal. So x is equal to a negative 4. Therefore, if we go back to the original expression, we are now going to have 5 raised to the power of the log of 1 over 16 to base of 2 is really equal to 5 raised to the power of negative 4. Again, using your rules for exponents, 5 to the power of negative 4 is 1 over 5 to the positive 4, which is equal to 1 over 625. And that corresponds with B as the multiple choice answer. Let's look at another example. Here we have to solve for x, where the log of x to base 16 over 25 is equal to a negative 3 over 2. Once again, in order to solve for x, we need to convert this to exponential form. We start off by using the base to the logarithm, 16 over 25, raised to the power of negative 3 over 2 is equal to x. Therefore, x is equal to, now once again we have a fractional exponent, which we could convert to a radical. That's the same as the square root of 16 over 25, all raised to the power of a negative 3. The square root of 16 over 25 is equal to 4 over 5, raised to the power of negative 3. So x is equal to, using another rule for exponents, 5 over 4 raised to the power of a positive 3. 5 cubed is equal to 125, and 4 cubed is equal to 64. So in this case, the value of x is equal to 125 over 64, and that corresponds to A as our multiple choice item. In example 3, we have what are referred to as nested logarithms. So I have 2 examples here, and I will solve both of these examples using a different method. Here, I will start off with the inside part. We can evaluate the log of 64 to base 4. So if we rewrite the number 64 with a base of 4, the answer will just correspond to the exponent. So let's do that. That will equal the log base 2 of the log base 3, and 64 will be written as 4 raised to the power of 3 with a base of 4. Continuing with this part of the example, the exponent 3. So we have the log of 3, and this will equal the log of 4 cubed to base 4 is just equal to 3. So now we have, and that's to the base of 2. So now we will evaluate the brackets again. So this time we will have, note that the base to your power is the same as the base to your logarithm. So the answer will equal the exponent. And when there's no exponent there, we can know that the exponent is equal to 1. So here we have the log of 1 to base 2. And we can rewrite the number 1 with a base of 2, because 2 raised to the power of 0 is equal to 1. So in this example, the answer is equal to 0. Now, in part B of this question, what we will do is we will let the log of the fourth root of 7 to base 7 to base 16, we will let that equal x. And what we will do now is we will take this outside logarithm, log base 16 of something equal to x, and we will convert that to exponential form. So we write it as 16 raised to the power of x is equal to that will be the log of the fourth root of 7 to base 7. So you can see here that this is getting complicated because what I could do here is I could still rewrite the fourth root of 7 with a base of 7. So we are on the right track here, but we're just taking another root. So what we could do here is we can rewrite the fourth root of 7 as 7 to the power of 1/4. So now we have 16 raised to the power of x is equal to 1/4. And in the back of our mind, we can see that we can express both sides of this equation with a base of 4. 16 is 4 squared raised to the power of x, and 1/4 is the same as 4 raised to the power of -1. So we have 4 to the power of 2x is equal to 4 to the -1. Since the powers are equal with the same base, we can conclude that 2x is equal to a -1. Therefore, x is equal to a -1/2. So that means that this whole expression then is equal to a -1/2, and that answer corresponds with A as our multiple choice item. There is more than one way to solve these or to evaluate these logarithmic expressions, so it just depends upon what rule you choose to use first. One of the outcomes of this course is that you have the ability to estimate the value of a logarithm. So I would like to do a couple of examples where we estimate the value of a logarithm. In this case, we will use to the nearest 10th. So in the first example, we are asked to evaluate the log of 12 to base 2. So let's let the log of 12 to base 2 equal x. When we convert it to exponential form, we have 2 raised to the power of x must equal 12. So if we start to guess and check, we know that 2 squared is equal to 4. We know that 2 cubed is equal to 8. We know that 2 to the 4 is equal to 16. So the value of 12 is somewhere between 8 and 16. So therefore, we can estimate that, let's say, 2 to the power of 3.5 is approximately equal to 12. Therefore, we're estimating that the value of x is approximately 3.5. Since 12 is halfway between 8 and 16. Now, in the meantime, let's go verify using a calculator how close we are with our estimation. So we do have to remember that the answer that we have here is an estimate. All right? To verify how close we are, let's say that the log of 12 to base 2 is equal to the log of 12 divided by the log of 2. When you do that on a calculator, the value that you get is approximately 3.58. But we're asked to round it off to the nearest 10th, which is approximately 3.6. So 3.6 would have been a closer estimate. However, when we estimate, we cannot always be guaranteed that our answer is correct. Let's look at another example. We are asked to estimate the value of the log of 80 to base 3 to the nearest 10th. So let's let the log of 80 to base 3 equal x. converting to exponential form, we have 3 raised to the power of x is equal to 80. Let's do some checking. We know that 3 cubed is equal to 27. We know that 3 raised to the power of 4 is equal to 81. So you know that the value of 80 is between 27 and 81, but it's closer to 81. So I would say here that the value of x could approximately be 3.9. Let's say that that would be our estimate. It's not exactly 81, but it's close to it. But just remember that the value that we're working with is an estimate and it's not an actual answer. So let's go again and verify using the calculator how close we are. So if we look at the log of 80 to base 3, we can evaluate that as the log of 80 divided by the log of 3. When you do that on a calculator, you will get approximately 3.99. And rounding that off to the nearest tenth, it's approximately 4.0. In the next example, this would be an example of a long answer question as opposed to a multiple choice item. We are asked to solve for x. So we will use all of the properties of logarithms that we have practiced so far. When we look at the first term, I see the square root of 8. And I know that I can rewrite the number 8 with a base of 2. In the next term, we have the cube root of 729. The cube root of 729 is equal to 9. And then I know that I can write the number 9 with a base of 3. In the third case, we can rewrite the number 1 over 32 with a base of 2. So the property of logs that we will use frequently throughout this example is this one. The log of c raised to the power of k to base c is equal to k. That's an important and useful property that is frequently used throughout this chapter. So let's continue with our solution. Here we would have 3 times the log of, we will change the root of 8 to be 8 to the power of 1/2 to base 2, plus 1/3 times the log of, the cube root of 729 is 9 to base 3, minus the log of 1 over 32 can be written as 1 over 2 to the power of 5 to base 2 equals x plus 6. So then we have 3 times the log of, the number 8 can be rewritten with a base of 2. 8 is the same as 2 cubed raised to the power of 1/2. Then we have 1/3 multiplied by the log of, 9 can be written as 3 squared since we have a base of 3. And 1 over 2 to the 5th can be written as 2 to the power of -5 equals x plus 6. So then we have in the next step 3 times the log of, that would be 2 raised to the power of 3 over 2 to base 2, plus 1 over 3. The log of 3 squared to base 3 is just equal to 2, minus the log of 2 to the -5 to base 2 is just equal to a -5, is equal to x plus 6. So then the first term simplifies to be 3 multiplied by 3 over 2 plus 2/3 plus 5 is equal to x plus 6. So then we have 9 over 2 plus 2 over 3 plus 5 minus 6 is equal to x. We can solve for x by finding the lowest common denominator, which is equal to 6 in this example. So continuing up on the other side of the screen, we would have x is equal to, if 6 is the common denominator, we have 27 over 6 plus 4 over 6. And minus 1 there, 5 minus 6 is a minus 1, which is the same as minus 6 over 6. 27 plus 4 is 31. 31 minus 6 is equal to 25 over 6 as our final answer. So here we are using the properties of logs throughout several terms in a logarithmic equation. And finally, we have another example where we are asked to determine the values of x and y if the log of 2x plus y to base 2 is equal to 0 and the log of x minus y to base 2 is equal to 3. What we need to do in order to find the values of x and y is to take each of these expressions and convert them to exponential form. So we have the log of 2x plus y to base 2 is equal to 0. Therefore, 2 raised to the power of 0 is equal to 2x plus y. 2 to the power of 0 is just equal to 1. So we have 2x plus y is equal to 1. In the second part, we have the log of x minus y to base 2 is equal to 3. Converting to exponential form, we have 2 raised to the power of 3 is equal to x minus y. Therefore, x minus y is equal to 8. And essentially what we've done here is we've set up a system of equations. And we can now solve that system of equations using the process of elimination. So we have 2x plus y equals 1, and x minus y is equal to 8. What we will do now is we will add those two equations in order to eliminate the variable y. So when we add the two equations, we get 3x is equal to 9. Therefore, x is equal to 3. Using substitution, we take 2x plus y is equal to 1, and we substitute in x equals 3. So we have 2 times 3 plus y is equal to 1. 6 plus y is equal to 1. So y is equal to 1 minus 6, and the value of y is equal to a negative 5. So this also solves for x and y using a system of equations by converting from exponential form, from logarithmic form to exponential form. These are just a couple of the properties that we use throughout this presentation. Converting from exponential form to logarithmic form is always useful in solving or in evaluating a simple logarithmic expression or equation. If a to the power of b equals c, then the log of c to base a is equal to b. The property that I think is most useful here, or one of the most useful properties, is if we can get the log of c to the power of k with a base of c. The base to the power is equal to the base to your logarithm, so the answer is equal to the exponent k. Note that the log of a to base c is equal to the log of a divided by the log of c. We also used our rule for converting with a fractional exponent to a radical. So if we have a raised to the power of m over n, that's equal to the nth root of a, all raised to the power of m. That property is used frequently as well. And the other properties, if we have two powers with the same base, if a to the m is equal to a to the n, then we know that the exponents must be equal. Therefore, m is equal to n. Similarly, if a to the m is equal to b to the m, so in this case the exponents are equal, so we realize that the bases must be equal. A must equal b. As well, if the log of a to base c is equal to the log of b to base c, then a must equal b. Thank you for your time and your attention, and hopefully you will continue with the review with the other sections in this chapter. Thank you.